For millions of years, the western edge of South America has functioned like a colossal geological collision zone, where an oceanic tectonic plate steadily dives beneath an entire continent. That slow motion, measured in only a few inches each year, has transformed Chile into one of the most earthquake-prone regions on Earth. It built the Andes Mountains, fueled chains of volcanoes, fractured vast sections of crust, and generated earthquakes powerful enough to send tsunami waves across the Pacific Ocean. But what exactly happens when a rupture begins far below the surface, deep inside a sinking tectonic plate, rather than along the seafloor itself? Why do some Chilean earthquakes trigger global disasters, while others mainly shake the interior of the continent? And why does northern Chile repeatedly experience powerful deep earthquakes beneath one of the world's largest copper-producing regions? Those questions returned with urgency after the magnitude 6.9 earthquake that struck near Calama in northern Chile on May 25, 2026. The earthquake occurred at a depth of approximately 68 miles, or 109 kilometers beneath the surface, placing it well below the shallow megathrust zone responsible for Chile's most devastating historical disasters. Even so, the shaking spread across the mineral-rich Antofagasta region, temporarily disrupting operations in the world's largest copper-producing district. Mining companies activated emergency protocols, inspections halted extraction activities, and localized landslides occurred in production zones carved into the desert mountains. Electricity interruptions and water supply problems briefly affected portions of Calama, a city built around one of the most productive mining belts on Earth. Yet despite the strength of the earthquake, the event did not escalate into a catastrophic surface disaster. That distinction is critical because the mechanics of this earthquake were fundamentally different from the gigantic shallow megathrust earthquakes for which Chile is infamous. The 2026 Calama earthquake was not primarily a rupture occurring at the direct boundary between the Nazca Plate and the South American Plate. Instead, the depth strongly suggests that the earthquake originated inside the descending Nazca slab itself, within a region of immense internal stress where the oceanic plate bends, compresses, dehydrates, and thermally transforms as it sinks into the mantle. Understanding why this earthquake happened requires looking far beyond the surface. Chile occupies one of the most tectonically aggressive environments on Earth because it lies along the western margin of South America, where the Nazca Plate converges with the South American Plate. The Nazca Plate moves eastward at rates between roughly 2 and 3 inches per year, equivalent to about 65 to 80 millimeters annually. That motion may sound slow on a human timescale, but in geological terms, it represents extraordinary tectonic velocity. Over centuries, the converging plates accumulate enormous elastic strain. Eventually, the crust can no longer sustain the stress, and the stored energy releases suddenly as earthquakes. The South American subduction zone extends for more than 4,300 miles, or 7,000 kilometers, along the continent's western edge. It begins near southern Chile, close to the Chile Triple Junction, and continues northward toward Panama. Along this immense tectonic boundary, the dense oceanic Nazca Plate dives beneath the lighter continental crust of South America. This process, called subduction, governs nearly every major geological feature of the Andes region. As the oceanic plate descends, it drags sediments downward, compresses the continental margin, and transfers massive stresses into the overriding crust. The Andes Mountains themselves are direct products of this prolonged tectonic collision. Volcanic arcs form because water-rich minerals trapped within the descending slab break down under increasing temperature and pressure. Those released fluids rise into the overlying mantle wedge, lowering melting temperatures and generating magma. The magma eventually ascends toward the surface, feeding volcanoes that stretch along much of western South America. But volcanic activity is not uniform along the arc, and neither is earthquake behavior. The geometry of the subducting slab changes dramatically from one region to another. In some segments, the Nazca Plate plunges steeply into the mantle at angles approaching 30 degrees. In others, the slab flattens and travels nearly horizontally beneath the continent for hundreds of miles before descending again. These flat slab segments strongly influence seismicity, crustal deformation, and volcanic distribution. Northern Chile sits within one of the steeply dipping slab regions. This geometry allows earthquakes to occur over a broad range of depths. Shallow earthquakes near the plate interface typically occur between 6 and 37 miles, or roughly 10 to 60 kilometers deep. These are often megathrust events capable of generating tsunamis because they displace the seafloor directly. Intermediate depth earthquakes, however, occur much deeper inside the descending Nazca Plate itself, generally between about 43 and 186 miles, or 70 to 300 kilometers deep. The Calama earthquake belongs to this intermediate depth category. That distinction changes everything about the rupture mechanism, the style of shaking, and the hazards involved. When oceanic crust first forms at mid-ocean ridges, it is relatively warm and buoyant. Over millions of years, the crust cools, thickens, and becomes denser. By the time the Nazca Plate reaches the Peru-Chile Trench, it has become heavy enough to sink beneath South America. Yet the plate does not descend smoothly. It bends downward sharply at the trench, creating immense extensional and compressional stresses within the slab itself. As the slab sinks deeper into the mantle, pressure and temperature increase dramatically. Minerals inside the oceanic crust begin undergoing metamorphic transformations. Water trapped inside hydrated minerals becomes unstable and is released through dehydration reactions. Those reactions are central to understanding many intermediate depth earthquakes. At depths near 68 miles or 109 kilometers, the descending slab experiences conditions where hydrated minerals such as serpentinite and amphibole begin breaking down. When these minerals release water, several important processes occur simultaneously. First, the released fluids reduce frictional resistance along fractures inside the slab. Second, dehydration weakens portions of the rock mechanically. Third, fluid pressure may increase rapidly inside confined zones, helping faults rupture suddenly. This phenomenon is known as dehydration embrittlement, and many seismologists believe it plays a major role in generating intermediate depth earthquakes beneath northern Chile. Unlike shallow crustal rocks, materials at these depths should theoretically deform plastically due to the enormous pressure and temperature. Yet earthquakes still occur because dehydration reactions can temporarily create brittle conditions, even deep inside the mantle environment. The Nazca Plate beneath northern Chile is especially prone to these processes because it carries large amounts of altered oceanic crust and hydrated mantle material downward from the seafloor. As the slab descends past 100 kilometers depth, dehydration reactions intensify. Internal stresses build from slab bending, thermal contraction, and gravitational sinking. Eventually, sections of the slab rupture catastrophically. That is likely what occurred beneath Calama. The earthquake's depth explains why it produced widespread shaking but limited surface destruction. Deep earthquakes radiate seismic waves across very large regions because the waves travel efficiently through cold, dense slab material. However, by the time those waves reach the surface, the most violent ground accelerations are often reduced compared with shallow crustal or megathrust events of similar magnitude. Even so, a magnitude 6.9 earthquake releases tremendous energy. Seismically, each whole number increase in magnitude represents roughly 32 times more energy release. Compared with a magnitude 5.9 event, the Calama earthquake released approximately 32 times more energy. Relative to a magnitude 4.9 earthquake, the difference becomes more than 1,000 times greater. Mining infrastructure in northern Chile is particularly sensitive to seismic shaking because operations often involve enormous open pits, steep excavation walls, underground tunnels, conveyor systems, tailings facilities, and electrical networks spread across rugged terrain. Even moderate shaking can trigger rockfalls or destabilize pit slopes. Temporary operational shutdowns following significant earthquakes are standard procedure because engineers must inspect structural integrity before resuming extraction. The Antofagasta region is central to the global copper supply chain. Northern Chile produces a substantial fraction of the world's copper, much of it extracted from giant porphyry copper systems formed through long-term magmatic processes associated with subduction. Ironically, the same tectonic forces generating destructive earthquakes also created the mineral wealth that transformed the region into a mining superpower. Porphyry copper deposits form when magma generated above subduction zones rises through the crust and releases metal-rich hydrothermal fluids. Over millions of years, those fluids deposit copper, molybdenum, gold, and other minerals within fractured rock systems. Without the Nazca Plate descending beneath South America, the geological conditions necessary for Chile's giant copper deposits would never have existed. This relationship between tectonics and mineralization is one of the defining geological stories of the Andes. The subduction system simultaneously creates economic opportunity and geological danger. Every major mining operation in northern Chile exists because of ancient magmatic activity tied directly to the same plate convergence, now generating earthquakes beneath the region. The 2026 earthquake also highlights the remarkable segmentation of seismic behavior along the Chilean margin. Chile has experienced nearly every known category of earthquake associated with subduction systems. Shallow megathrust ruptures occur along the plate boundary itself. Crustal earthquakes develop within the overriding South American plate. Intermediate depth earthquakes occur inside the Nazca slab. Even deep focus earthquakes exceeding 300 miles or 500 kilometers depth occur farther east beneath Bolivia and Argentina. The most famous of all remains the May 22, 1960 Valdivia earthquake, the largest instrumentally recorded earthquake in human history. That magnitude 9.5 megathrust rupture devastated southern Chile and generated a trans-Pacific tsunami that reached Hawaii, Japan, and the Philippines. The event illustrated the terrifying scale of energy accumulation possible along the Nazca South America plate boundary. But the Valdivia earthquake was fundamentally different from the Calama event. The 1960 rupture occurred on the shallow megathrust interface where the two tectonic plates were locked together. During centuries of strain accumulation, the overriding South American plate had become elastically compressed and warped. When the fault finally ruptured, enormous sections of the seafloor shifted vertically, displacing ocean water and generating the tsunami. The Calama earthquake occurred much deeper and within the descending slab itself. Because of its depth, it lacked the capacity to significantly displace the seafloor. That is why no major tsunami occurred despite the strong magnitude. Chile's earthquake history demonstrates how subduction zones can produce radically different seismic hazards depending on rupture location and depth. A shallow offshore earthquake may trigger devastating tsunamis and violent coastal shaking. A deep intermediate depth earthquake may shake a vast inland region while producing comparatively limited surface destruction. Both originate from the same convergent plate system, yet their impacts differ enormously. Northern Chile is especially important for studying intermediate depth seismicity because earthquakes there cluster within a well-defined Waddati-Benioff zone. This inclined seismic zone traces the descending path of the Nazca slab into the mantle. By mapping earthquake depths and locations, geophysicists can effectively visualize the geometry of the subducting plate beneath South America. The Calama earthquake occurred within one of the most seismically active intermediate depth segments of this zone. Similar earthquakes have struck northern Chile repeatedly over modern history, including the major 2005 Tarapacá earthquake, which reached magnitude 7.8. That earthquake also originated within the descending slab at intermediate depth and caused widespread shaking across the region. Scientists continue debating the exact physical mechanisms responsible for intermediate depth earthquakes because the environmental conditions at those depths challenge conventional models of brittle faulting. At shallow depths, rocks fracture because confining pressure is relatively low. At depths exceeding 60 miles or 100 kilometers, however, pressure should theoretically prevent ordinary brittle failure. Several competing or complementary mechanisms may explain why earthquakes still occur there. Dehydration embrittlement remains one leading theory. Another involves transformational faulting, where minerals undergo rapid phase changes that suddenly weaken portions of the slab. For example, olivine may transform into denser mineral structures under high pressure, potentially creating localized instabilities. Thermal shear runaway, is another proposed mechanism in which rapid deformation concentrates heat, lowering rock strength catastrophically. The Nazca slab beneath northern Chile provides an ideal natural laboratory for studying these processes because the subducting plate remains relatively cold compared with surrounding mantle material. Cold slabs can maintain brittle behavior deeper into the mantle than warmer slabs elsewhere. That helps explain why deep and intermediate depth earthquakes are so common beneath parts of South America. The geometry of the coastline near northern Chile also plays a role in concentrating seismicity. The bend between Peru and Chile corresponds with changes in slab dip angle, stress orientation, and tectonic segmentation. Many intermediate depth earthquakes cluster near this transition zone. Variations in slab geometry influence how stress accumulates and how fluids migrate through the descending crust. One of the most fascinating aspects of subduction beneath Chile is the existence of flat slab regions farther south. In these segments, the Nazca Plate descends at extremely shallow angles, sometimes less than 10 degrees. Instead of plunging steeply into the mantle, the slab travels horizontally beneath South America for hundreds of kilometers. These flat slab regions suppress volcanism because the shallow geometry disrupts the mantle wedge processes necessary for magma generation. At the same time, they transmit compressional stress far inland, producing broad zones of crustal deformation. The contrast between steep and flat slab segments helps explain why volcanic activity and earthquake behavior vary dramatically along the Andes. Northern Chile's steep slab geometry supports active volcanism and deep seismicity simultaneously. Volcanoes in the central volcanic zone owe their existence to fluids released from the descending slab, while intermediate-depth earthquakes reflect the slab's ongoing internal deformation. The Atacama Desert itself also reflects long-term tectonic and climatic interactions. The uplift of the Andes helped establish atmospheric circulation patterns that contributed to extreme aridity along the Pacific margin. Some portions of the Atacama receive almost no rainfall for years at a time. Yet beneath this hyper-arid surface lies one of the world's most tectonically dynamic crustal environments. Mining operations there must account constantly for seismic risk. Modern Chilean engineering standards are among the most advanced globally because the nation has accumulated extensive experience with major earthquakes. Structures, pipelines, and industrial systems are routinely designed with strong seismic resilience in mind. The relatively limited infrastructure damage following the Calama earthquake reflects both the depth of the event and Chile's long investment in earthquake-resistant engineering. Still, the geological threat remains permanent. Subduction along the Chilean margin has persisted for tens of millions of years and will continue far into the future. Every year, additional strain accumulates. Every year, the Nazca Plate sinks deeper beneath the continent. Every year, stresses intensify within both the plate boundary and the slab interior. The 2026 earthquake serves as another reminder that Chile's seismicity is not governed by a single fault or isolated tectonic process. Instead, it reflects a deeply interconnected system spanning hundreds of miles beneath the continent. Surface topography, volcanism, mineralization, crustal deformation, and earthquake generation all originate from the same underlying engine of plate convergence. For science enthusiasts, few places on Earth illustrate plate tectonics more dramatically than Chile. The country effectively exposes an active continental margin in real time. One can trace the full tectonic cycle there. Oceanic crust forms at distant spreading ridges, migrates eastward across the Pacific, descends beneath South America, generates magma, uplifts mountains, fractures crust, and ultimately recycles into the mantle. The Calama earthquake represents one moment within that enormous geological cycle. Deep inside the Nazca slab, stresses accumulated over decades until rock strength failed abruptly. Seismic waves radiated outward through the Andes and the desert mining districts. Pits halted operations, slopes shed debris, power systems flickered. Yet the deeper significance of the event lies beneath the surface, inside the mechanics of subduction itself. Chile's future earthquakes are inevitable because the tectonic engine driving them remains fully active. The exact timing of major ruptures cannot yet be predicted, but the broader geodynamic framework is unmistakable. Intermediate depth earthquakes will continue occurring beneath northern Chile as the Nazca Plate descends and dehydrates. Megathrust earthquakes will continue rupturing segments of the plate interface where strain accumulates. Deep focus earthquakes will continue occurring farther inland as the slab penetrates deeper into the mantle. What makes Chile extraordinary is not simply the frequency of earthquakes, but the sheer diversity of tectonic processes operating simultaneously beneath the region. Few places on Earth display such a complete spectrum of subduction-related phenomena. From shallow tsunami-genic ruptures to deep mantle earthquakes, from active volcanoes to giant mineral systems, the Andes margin compresses an immense range of geological mechanisms into a single continental boundary. The magnitude 6.9 Calama earthquake may not enter history alongside the colossal 1960 Valdivia disaster, but scientifically it remains profoundly important. It offers another glimpse into the hidden mechanics of the Nazca slab and the immense tectonic forces shaping Western South America. Every intermediate depth earthquake provides valuable seismic data that helps researchers refine models of slab deformation, fluid release, mantle dynamics, and earthquake generation under extreme conditions. And beneath the deserts of northern Chile, the process continues uninterrupted. The Nazca Plate keeps sinking. Minerals continue dehydrating. Stresses continue accumulating. Deep faults continue evolving in darkness far below the mines and mountains. The earthquake that shook Antofagasta was not an isolated anomaly. It was one pulse within a planetary-scale tectonic system that has operated for millions of years and will continue long after modern cities, mines, and infrastructure disappear from the surface above.